Welcome to my new calculus channel. My name is John Gabriel, and you'll recall that in the previous video we laid all the foundations for the straight line, and we had to think a lot about the philosophy of everything that we were going to use to define the straight line. So we had to think of things like location, motion, position, and lots of other things, right? And so we talked about direction, we talked about how to identify objects. Now, I know that in the previous video I talked about creating light. You don't actually have to create light. I did that because it made it easier for me to realize the notion of path, which is, by the way, inanimate. It doesn't matter that anything exists or not. But of course, in an empty universe, even a location wouldn't make much sense, would it? So if you think about it, you can't even begin to define location in an empty universe unless you do it using the fact that something exists as an origin, which leads to a elementary kind of reference point, right? So let's continue now with the next part of this series, and we'll carry on where we left off. So I'll come back to that diagram in a moment. So remember I said we're in a conundrum because there are so many paths, and it's daunting to think about the relationship between any of these two paths. So if you look at this particular diagram, it illustrates the idea. So if we are here, where we are, and something else is not here, where this yellow ball is, or let's call it a little star or a sun, then there are many ways or paths to get to this ball. And it doesn't matter whether you're thinking about it in terms of a dimension or a multiple dimension. All that matters is that we have defined motion, and so we could say motion from here to here is a change in position, right? And so on. And so we can have an infinite number. I wouldn't want to say infinite number, but we can have countless number of paths, right? And so out of all these paths, it turns out that many of them can be equal. For example, if they're symmetrical about this shortest distance, but we don't want to go there just yet. But if they're symmetrical, then they're equal. And out of all the paths, there is only one distance that is the shortest. So it's unique, right? Now, we can call all the paths the same or equal if the change or movement from the source location to the destination location involves exactly the same movement. In other words, all the different here to not here movements. Okay? And so from this we realize the concepts of less or more movements or motions, shorter or longer in any given path. So this reasoning leads us to the possibility of the existence of a path requiring the least changes or movements, right? And from this we infer that the path consisting of only those same movements from start location to finish location is the shortest path. And of course, we call the shortest path a straight line. Now, you cannot see a straight line, right? So again, to one of my commenters who talked about requiring light, it doesn't matter whether you have light or not. You cannot see this line here, right? Because you just as you can't see a distance. Can you see a distance? No, because distance isn't something that can be seen. So we arrive at the very first requirement, which is a straight line. And notice that we did this without any consideration of number or any other geometrical object. And the only thing that we used, the only object that we used, was the idea of point or location. And so we arrive at the notion of a straight line. Now, there is no such thing as an infinite line, by the way. That is just nonsense. A line is the distance between 2 points. So why can you not have an infinite line? Because an infinite line doesn't have endpoints. So what are you talking about if you're not talking about distance with an infinite line? You see how ridiculous it is to talk about an infinite line? You can't have an infinite distance. There's no such thing, okay? So now, notice that for the first requirement, we haven't mentioned dimensions, such as plane or space or anything else. And in fact, we can't talk about these until we realize the concept of circle, which can only be realized after the second requirement. So what does the second requirement say, and how does it help us to realize the concept of a circle? So now the second requirement tells us that we can extend a line or a straight line in either direction, okay? So that's very important, as you'll see when we get to the concept of a circle. In fact, if we cannot extend a straight line, it's impossible to define the circle just based on the notion of straight line. You can't say rotate it around the point, because what does rotation mean? It's nonsense. It doesn't mean anything. And you can't talk about a plane or anything, because we'll only get to those concepts after we have the concept of a circle. So till this stage, we have realized the primitive concepts of point and straight line. And I've been moving very slowly because it's very difficult to derive the first three requirements. That is, the straight line, the extended line, and the circle. Now, how is it possible to know that a line can be extended? Well, it's very easy to see that you can extend a line. Well, the very motion from here to not here, let's say up here, or here to not here on this path, means that we have a shorter distance, right? And we already know that you can have a shortest distance between two objects. So therefore, we know that if you can have a shorter path, it must be possible to extend it and also to reduce it. Okay? So we're done with that graphic. And that's pretty straightforward. And now, we can show that any path between 2 points, okay, we've done that, so I don't want to repeat that. So now we have enough prior knowledge to realize the concept of a circle. Now notice, this is where it becomes extremely beautiful, by the way. And things start falling into place very easily now that we have the first two requirements. So you might first say that a path from which any path to a given center is the same straight line is a circle. But then, do you see these little red paths on the surface of these spheres? All of these would be circles by that definition. Okay? So paths produced in this way may look nothing like a circle, but they're circles by that definition. So for example, any complete path on a sphere will meet the requirement if we're using the requirement for circle if we're using this definition. So that is insufficient, and this is where requirement 2, extending a straight line, comes into play. We can realize a circle distance or a path as a path from which the shortest path to a given point, which we can call a center, is the same straight line, and that if any such straight line is extended by the same straight line, it will again meet the circle path. Okay, so in other words, it's definitely going to be a circle if we go to the center and we extend that straight line and it joins the path once again. Otherwise, it wouldn't join the path ever again, and it's not a circle. So at this stage, we can give the special straight line that is used to define circles the name radius, okay? And if the straight line is extended from one point on a circle to another, we can call the straight line a diameter. And from this now we are able to realize the concept of a plane as follows. We can say that a plane, which is one-dimensional or two-dimensional, rather, consists of paths which are part of the same circle if the circle is extended indefinitely in any direction by obviously extending its diameter. So now we've derived a lot of objects, but and although we have systematically established the first three requirements of Euclid's elements, we have a long way to go before we can deal with the fourth requirement, okay, which says that all right angles are equal. Okay, so we need quite a few more definitions before we can do this. And we need to define things like angle, which, by the way, is defined in terms of a circle, and things like symmetry, which, again, by the way, is defined in terms of a circle path, and things like an arc. Okay, so an arc is any part of a circle's path. All right, so, and I'm going to stop here, but in the next video I'll continue. How do we know that a circle paths from one end of a diameter to the other end are the same? In other words, we're talking about symmetry here. And so we'll deal with that in part 3. Okay. Well, I hope that you're all doing well. Today I'm not really feeling that great. And I don't even know how I managed to record this video. But I was feeling pretty awful when I woke up, and I have a lot of health issues. So, at any rate, become a subscriber if you're not already a subscriber, and keep track of this series so that you'll see how beautiful and how logically and systematically I will arrive at right angles and also at parallel lines long before we get to the fifth requirement, which is incorrectly known as the parallel postulate or as the fifth postulate. So I'm going to leave you with that now. My name is John Gabriel. This is the New Calculus channel. Till next time, goodbye, friends.